In this lesson, we're going to learn how to expand some binomials raised to powers using a couple of different methods. One of them using something referred to as Pascal's triangle, and another one referred to as the binomial theorem. Now, what exactly is a plus b to the power of n? Well, I'll tell you one thing that it's not. What a lot of students will do is that they'll distribute that exponent and say that it's the same as a to the power of n plus b to the power of n. But we should see, if we just pick a quick example, maybe choosing a to be 3 and b to be 4, that this isn't going to be true, because 3 plus 4 is 7, while 3 squared and 4 squared separately are 9 and 16. So notice that 49 is not the same as 25. So in general, we're not able to distribute that exponent if there's ever addition inside of parentheses. So what exactly is a plus b to the power of n? Well, it's a plus b times itself n times. So a plus b times a plus b times a plus b, and so on. So why don't we take a look at the first few expansions to see a pattern that starts to emerge. Notice that anything to the power of 0 is always equal to 1. So the 0 power is a pretty simple process. A plus b to the power of 1, well, anything to the power of 1 is itself. So that's just a plus b. But I'm going to go ahead and put 1s in front of the a and the b to indicate that those coefficients are in fact 1. So let's take a look at a plus b quantity squared. Well, notice what that means. It means a plus b times a plus b. So now we just apply the distributive property to get a squared plus 2ab plus b squared. And notice again that the first and last terms have coefficients of 1. Well, what if we were to multiply a plus b times itself 3 times? Well, what we should realize is that we've already figured out what a plus b times itself twice is. So we could replace a plus b to the third power as a plus b times the quantity that we just found, which is a squared plus 2ab plus b squared. So each time we raised or multiply by another a plus b, we're just multiplying by the previous result. Now notice this is pretty simple to do once you get the hang of it, because we're multiplying a to each of the 3 terms, which simply makes each of these exponents on a 1 larger. Now we're multiplying b to each of these terms, which makes the exponent on b 1 larger. And now we should realize that we have a couple of like terms that can combine here. We have some a squared b terms. We have some ab squared terms. So here we have 1 of these a cubes, 3 of these a squared b's, 3 of these ab squareds, and 1 of these b cubes. And again, the first and last terms have coefficients of 1. Well, you might already be starting to see some patterns where each of the terms has some a's and b's. We see that some of the coefficients are interesting based off of the exponents that we're raising to the power. But let's take a look at a plus b to the 4th to see if we could really nail down a couple of patterns. Well, a plus b to the power of 4 is a plus b times the quantity we just found. So now again, if we distribute a to each of the terms in the second parentheses, then that just increases each of the a exponents by 1. And if we distribute the b to each of the terms inside, that ends up giving me an extra b on each term. Now you can see that what I'm doing here as I distribute is lining up the like terms. I get some a cubed b terms, some a squared b squared terms, some ab cubed terms, and now if we combine them together, we get this quantity. Notice again that the first and last terms have a coefficient of 1. Now this is what we would do if we were really going to multiply this out every single time. But notice that this is not always a plus b. Maybe it's 3x minus 2y. And then at that point, we have a lot more work to do to be able to distribute. But it turns out that there's a shortcut. Let's go ahead and take a look at a few of the patterns that are starting to emerge here. Well, if we take a look at the results that we got from the expansions, we ended up getting these quantities right here. Now, a couple of things to notice here. If you look at each of these quantities, we should recognize that every time we multiply by one more exponent, we end up getting one more term. So if this first row is considered row 0, it has one term. Row 1 has 2 terms. Row 2 has 3 terms. Row 3 has 4 terms. Row 4 has 5 terms. So that's one pattern that we should recognize. We can also see that the quantities here, the first term is a to the power of n, and the last term is b to the power of n, which means if I was expanding a plus b to the power of 4, we should realize the first term is a to the 4th, and the last term is b to the 4th. Well, let's take a look at another pattern. Let's look at the exponents of a and b in each of the terms. Let's just take a look at the last line, the a plus b to the power of 4. Let's look at each term of this expansion and recognize that a to the 4th is the first term, and each term drops down by one exponent. So the second term has a to the power of 3. The third term has a to the power of 2. The next term has a to the power of 1. And of course the last term has no a's. Now we can see the same thing happening if we look at the b's. As the a terms in this last expression decrease by one exponent, the b factors here increase by one exponent. So we could see the last term has 4 b's, b to the 4th, while the prior term has b to the 3rd, the prior term has b to the 2nd, the prior term has b to the 1st, and of course the first term has no b's. Now there's something else we should recognize as well, is that each of the exponents at each term add up to n, add up to this exponent. So if the exponent is 4, then the sum of each exponent should be 4. 3 plus 1 is 4. 2 plus 2 is 4. 1 plus 3 is 4, and so on. So as the exponents of a decrease by 1, the exponents of b increase by 1, which is what we just recognized. But now we should take a look at the coefficients, all of the red coefficients here. We should realize that in this expansion, we're going to see a rectangular array or collection of numbers that are following some pattern referred to as Pascal's triangle. We're going to go ahead and take a look at how these show up in more detail when we look at Pascal's triangle in the next slide. So if we start, first of all, with a triangle of ones, then what we're going to recognize is that by adding each of these terms, 1 plus 1, we're going to get the term just below it. So let's take a look at this from the beginning. If we start with this little triangle of ones, and I add 1 plus 1 together, I get an answer of 2. Now all the time I'm going to go ahead and put 1s along the diagonals if there's nothing left to add to the left and right. And now let's go ahead and come up with our next row. 1 plus 2 gives me 3. While 2 plus 1 also gives me 3. And now we put 1s along the diagonals. Well, let's think about why we put 1s on the diagonals real quick as well. Technically, we are adding two numbers together. But there is nothing to the left or right of each of those values on the ends, so we're really just adding 0, which is why we can now just put the 1s on the diagonal. Now let's take a look at the next row, row 4. 1 plus 3 is 4, but so is 3 plus 1. And now we realize that the 3 plus 3 in the middle is 6, therefore giving me 1s on the diagonals. And what you should see at this point are the coefficients of the expansions that we just came up with for a plus b to a power. So let's continue. We could see 1 plus 4 is 5, and 4 plus 1 is 5. And then, of course, 4 plus 6 and 6 plus 4 are both 10. And we put 1s along the diagonals. So we should see in every row there's going to be symmetry from the left side and the right side. If we take a look at 1 plus 5 is 6. 5 plus 10 and 10 plus 5 both give 15. And finally, 10 plus 10 is 20 in the middle. And the outsides are 1. We could continue this forever. Notice that every time we do this, all we're doing is coming up with the coefficients of a plus b to that power. So this row that we have right here that has the second term of 7 is the coefficients for the expansion a plus b to the power of 7. So without having to expand all the way out by multiplying a plus b times itself over and over and over, we can simply come up with all of the coefficients using Pascal's triangle. Now, Pascal's triangle has some really interesting patterns that show up. The first one we noticed automatically, which is symmetry. But that makes sense because if you're adding by the commutative property, let's say 4 plus 6 or 6 plus 4, they're both going to equal 10. But now we should recognize something else as well. If you take a look at any row here, any of these rows can be added up. If you take a look at all of the terms in each row, let's look at the row with 1, 4, 6, 4, and 1. If I add those terms up, I get an answer of 16. Let's look at the row 1, 2, 1. If I add those up, I get an answer of 4. If I add the results of all rows individually, you'd start to realize that you get powers of 2. 1 is 2 to the power of 0. 2 is 2 to the first. 4 is 2 to the second power. 8 is 2 to the third power. 16 is 2 to the fourth power, and so on. So notice that there's a pattern where if we add up all of those results, we get the powers of 2. If we look at the diagonals, we could see that the diagonal on the 1s, or is 1s along the first diagonal. The second diagonal is always going to be the counting numbers, 1, 2, 3, 4, 5, 6, 7. And this third row is actually going to be what we refer to as the triangular numbers, which are the number of dots that you would need in order to create equilateral triangles. You can look that up on your own. Another really interesting pattern is that of the Fibonacci sequence. Now, the left side, this left column over here, indicates what the Fibonacci sequence is. It's 1, 1, 2, 3, 5, and so on. And this is found by simply adding together the first two terms, 1 plus 1, which gives 2. If I then add 1 plus 2, I get 3. If I add 2 plus 3, I get 5. 3 plus 5 gives 8. 5 plus 8 gives 13. 8 plus 13 gives 21, and so on. And it turns out, if you look at these very special diagonals here with these different colors, the sum of those interesting diagonals are the terms of the Fibonacci sequence. We could also do another pattern here. Turns out that if you start at any value of 1, and start adding diagonally, let's look at the yellow one. 1 plus 3 is 4. 4 plus 6 gives 10. 10 plus 10 gives 20. That will always equal the value directly below it, referred to as a hockey stick. You could do this for as far as you want, add 5, 6, 7, 8 terms, and this same pattern would occur. We could also see another one. If you take a look at this second diagonal here, if you were to square each of those values, let's say 4 squared, that would actually be the same value as the 2 in the next, or the sum of the two values in the next column. And I encourage you to try that out and see for yourself. But I think one of the most intriguing results is something referred to as Sierpinskis Triangle. Sierpinskis Triangle is a self-replicating pattern. This is referred to as a fractal. Let's say that we start with this first black triangle. And we take the midpoint of each side and we cut out the triangle that attaches those midpoints. We now get 3 separate black triangles that are all connected. But now let's look at each of those individual black triangles and pluck that little triangle out of the middle. And now I get the third shape. But if I now take each of those minuscule black triangles, I now have 9 of them, pluck out the little white triangle in the middle, And I now get the same pattern. And this pattern can replicate itself over and over and over. This is a really interesting pattern called a fractal or Sierpinskis triangle. Well, let's take a look at Pascal's triangle and realize that if you look at all of the values that are even and odd, all of the even and odd values turn out to be representing Sierpinskis triangle. And notice that this will continue forever. If you look at the Pascal's triangle over and over and over, row by row by row by row by row, Sierpinskis triangle replicates itself in infinite rows. So this, I think, is one of the most intriguing patterns. But notice that there are numerous patterns, and Pascal's triangle is used in quite a few different areas of mathematics. But what we're going to use it for is simply for expanding binomials. So let's take a look at 3x plus 4 to the power of 4. Well, first of all, this means 3x plus 4 times itself 4 times. But I don't want to have to multiply that out 4 times, so instead we're going to use the patterns that we just learned. We could think of this as a plus b to the power of 4, where a is equal to 3x and b is equal to 4. Well, if we remember the pattern, remember that the terms involve the values of a, where the exponents decrease by 1. So the first term has a to the 4th, the second has a to the 3rd, and so on. While the b's tend to increase by 1, where the first term has no b's, the second term has 1 b, the third term has 2 b's, and so on. And lastly, the coefficients come from Pascal's triangle. So because the power is 4, I know that I'm going to be raising to the power of 4, and therefore these, looking at Pascal's triangle in row 4, is going to be 1, 4, 6, 4, 1. So at this point, we just plug in a and b, which are 3x and 4, to the indicated locations. Replace all of the a's with 3x, all of the b's with 4, and notice that I get these individual terms. I think it's easiest to actually write the expansion using a and b, and then plug in all of our values for a and b next. At this point, we have a few quantities that are raised to powers. So the first thing we have to do is apply the exponents within each of the terms. So we first of all look at 3x to the power of 4 and realize that that's 81x to the 4th. In the next term, we see 3x to the 3rd power. So 3 cubed and x cubed gives me 27x cubed. For the next term, we see 3x quantity squared, which is 9x squared, and 4 squared gives me 16. In the next term, we have 4 cubed, which is simply 64. And 4 to the power of 4 in the last term gives me 256. So now I see no more quantities that I have to raise to exponents. And so at this point, we simply multiply the coefficients in each term, and therefore 1 times 81 gives 81x to the 4th. In the next term, we multiply 4 times 27 times 4, which gives me 216. The next term, 6 times 9 times 16, gives me 864. Notice that that gives me an x squared term as well. Next term, 4 times 3 times 64 gives 768x. And finally, 1 times 256 gives 256. So you should realize that although I could have multiplied 3x plus 4 times itself 4 times, that would have gotten pretty challenging after a short amount of time because of the values that I'd be multiplying. If I use the pattern in the binomial expansion, I'm able to get there in the same way. Now we could go about this process in a slightly different way without using Pascal's triangle, using something referred to as factorials or combinations. Now a factorial is simply a positive integer, which we denote with an exclamation point. That's the product of all the integers from 1 up to that number. So let's take a look at what n factorial means. That just simply means n times 1 less than n times 2 less than n times 3 less than n, all the way until we get to 1. So as an example, if we wanted 7 factorial, we would just simply multiply 7 times 6 times 5 times 4 times 3 times 2 times 1. And that value gives me 5,040. Now this result is important because if we want to find the coefficients of Pascal's triangle, or the coefficient of each term in the expansion of a binomial, we can use these combinations to determine that coefficient. Now the notation for this is C of n choose r, or NCR. We could also write it in parentheses as n and r, where n is the total number of objects, and that's going to indicate the exponent of our expansion, while r is the number that we choose, which will be indicating the value in our expansion that we want, or the term that we want. Now the reason we learned about factorials is that in order to compute this quantity, we're simply using the factorials of n factorial in the numerator, r factorial is in the denominator, but the denominator will also have another factor of n minus r factorial. Let's take a look at a cool example that would allow us to use these combinations. So let's try to find out how many 5-card poker hands can be formed with a regular deck of 52 cards. Now, even if you don't know how to play poker, the point of this is that you can come up with 5 different cards within any 52-card deck. How many different 5-card combinations can you get? Well, the first thing to recognize is that there's 52 total cards, so that's n. We're trying to choose 5 cards, so that's going to be our r value. So we can write this as 52 choose 5. And by multiplying or working this out with our factorials, we could see that the 52 factorial goes in the numerator, 5 factorial goes in the denominator, and 52 minus 5 factorial also goes in the denominator. So the first thing we do is just recognize that 52 minus 5 is 47, and now because of these factorials, we just have to start multiplying 52 times 51 times 50 times 49 all the way down to 1. Now that would take a lot of time and a lot of paper to have to do that. So what we should also recognize is that the denominator of 47 factorial is actually going to cancel. Because notice that from 47 down to 1 is going to be in the numerator and also in the denominator. So you can cancel those directly. Now you can start to cancel each of the factors in the denominator as well with certain quantities in the numerator, or you could just multiply the result at this point. And when you divide, you're going to get 2,598,960 different possible 5-card combinations in a 52-card deck. Now, instead of having to calculate and count every single one of those, this formula allowed us to find that result. So let's take a look at why this is important for binomial expansions. The binomial theorem is what we're going to be using in order to use combinations or factorials to find the coefficients that Pascal's triangle actually found for us originally. So we're going to take a couple of examples here, or an example to take a look at what's going on. Now remember that when I was expanding a plus b to the power of n, the first term was a to the power of n and it had no zeros. The second term was 1 less than the a to the power of n, so if it was a to the 4th, the next term would have 3 a's. But now notice that the b's increase by 1. Notice the exponent in the next one. Notice the exponent on a is 1 less than the prior term, while the exponent above b is 1 more. So that pattern here doesn't change. That same pattern is going to occur with the binomial theorem or the process of using Pascal's triangle. What is changing is the coefficient. Notice that the coefficient has an n value, that's the original total, or the exponent, while the second value, the r value, is going to be the value we choose. In other words, we should recognize that since the exponent here is n, that's going to be my original total in all of my combination formulas. Since this is the 0 term, then the value in the bottom here of my combination is 0. Since this is the first term, my bottom number is 1. Since this is the second term, my bottom number is 2. And so notice that this continues all the way until we get to the final answer. Now, although this binomial theorem looks very complicated because of all the a's and b's and n's, all we're looking at is the pattern on the a's, where the a's are decreasing by 1 exponent each time, the b's are increasing by 1 exponent each time, and the coefficients can be found by these combinations. So one thing to recognize is that r, in choose r, or the r value in each coefficient, is the position that we're in within that expansion, but it turns out to also be the exponent above b. So let's take a look at an example and see how this can be a lot easier when you see it in a practical sense. If I let a be 2x and b be -3, then what I can recognize here is that the first term, since the exponent is 3, since it's 2x minus 3 to the power of 3, I know that my coefficient is going to be 3 choose 0. Next, we're going to get 3 choose 1. Next, we'll get 3 choose 2. And next, we'll get 3 choose 3. But notice that the pattern of a's and b's was exactly the same as it was when we were dealing with Pascal's triangle. The a's started with a to the third, ended with b to the third, and as a's decreased, b's increased. Now we should just recognize that each of these terms has a particular name. Term 0 is the first term, and that's simply because of the fact that the r value is 0. This is another reason why if I'm expanding something to the power of 3, I'm always going to get 4 terms. Or if I raise something to the power of 6, I'm always going to get 7 terms. Now what we should recognize is that anything to the 0 is 1, so those terms a to the 0 and b to the 0 should cancel. So now we can expand this by just using our formula. 3 choose 0 is simply 3 factorial, or n factorial, over 0 factorial, which is r factorial, times 3 minus 0 factorial, which is 3 factorial. And notice that I just replaced a with 2x. Notice for the next term, a is 2x and b is -3, but now we write out our formula here. 3 factorial is on top, 1 factorial is in the bottom, and now I have 3 minus 1 factorial, which is 2 factorial. For the next term, a becomes 2x, b becomes -3, and my coefficient becomes 3 factorial over 2 factorial times 3 minus 2 factorial. And lastly, b becomes -3, so we're left with 3 choose 3, which is 3 factorial on top, over 3 factorial in the bottom, times 3 minus 3 factorial in the bottom as well. So now we just have to figure out what each of these coefficients are, recognize that 3 factorial is 3 times 2 times 1, which is 6. 0 factorial, by definition, is 1, because it's basically saying how many different arrangements are there for 0 objects, and there's really just 1. So the definition for 0 factorial is 1. And finally, again, 3 factorial is 3 times 2 times 1, which is also 6. At the same time, we applied the exponents to get 2x to the power of 3, which is 8x cubed. And now we move on to the next coefficient. Here we have 3 factorial, which is 3 times 2 times 1, or 6. 1 factorial is 1, and 2 factorial is 2 times 1. Notice that 2x to the power of 2 is 4x squared times -3. And now if we do that same thing for the next one, we should realize that this coefficient will be the same as this coefficient, because the only difference is the order in which we're multiplying in the denominator. And lastly, this last coefficient should be the same as the first coefficient, because the only difference is the order we're multiplying in the denominator. And now if we just simply multiply each of the coefficients, we should realize that 6 over 6 is 1, 6 over 2 is 3, 6 over 2 is 3, and 6 over 6 is 1. 1, 3, 3, 1 were the same exact values that row 3 gave us when we looked at Pascal's triangle. So when we multiply each of these terms, the first term becomes 8x cubed. Here we have 3 times 4 is 12, times negative 3 is negative 36, x squared. Here we have 3 times 2 is 6, times 9 gives 54, so 54x. And finally, 6 over 6 is 1, times negative 27 is negative 27. So we really have multiple ways to do an expansion of some binomial to a power. We could multiply that binomial times itself over and over and over, but that's always going to be a long process to use. So the other two options we have are expanding using the patterns of A and B, using either Pascal's triangle or combinations in order to find the coefficients for our value.